Okay, so today we're going to continue talking about algorithms, but today we're actually going to use the algorithms to do some actual counting. In other words, we're going to put some numbers on these things. So how do we actually count things using algorithms? So here's the procedure. So to count something, we use the following procedure. Step one is you write a counting algorithm which generates the things you're trying to count. A good counting algorithm must have certain properties. We'll talk about that more in a moment, but for now, just understand that there are bad counting algorithms. Step two is for each step in the algorithm, you ask, how many choices do we have? Okay? So for each step, you say, how many choices do I have at this step? And then step three is you multiply the number of choices for each step together. And that's it. Okay, so let's see an example. So example, we've seen this one before or something similar. A fast food restaurant offers a combo meal consisting of a sandwich, side, and drink. Suppose there are 5 sandwiches, 3 sides, and 7 drinks. How many combo meals are possible? Well, we're going to have to write a counting algorithm, right, which generates all of the possible combo meals. We actually did this in the last lesson. One good algorithm would be step 1, choose your sandwich, step 2, choose your side, step 3, choose your drink. And what you have to do is figure out how many choices you have at each step. Well, at step 1, choosing your sandwich, there are 5 sandwiches to choose from, so you have 5 choices. Step 2, when you choose your side, well, there are 3 sides to choose from, so you have 3 choices. And for drink, you have 7 choices. So the total number of possible combo meals is obtained by just multiplying each one of these numbers together. The 5, the 3, the 7, and 5 times 3 times 7, that gives you 105. And that's kind of it. I said a moment ago that good counting algorithms have to have certain properties. In order for this procedure to function, the algorithm has to be of a certain type. I'm just going to say that that's a good counting algorithm. The algorithm has to be good. So let's talk about what that means. So the above procedure only works if your counting algorithm satisfies 2 properties. So this is what I mean by a good counting algorithm. Property 1 is that it generates every possible outcome exactly once. And that's it. It doesn't generate any prohibited or impossible outcomes. And it doesn't generate the same outcome multiple times. If you think about it, this has to be true because, basically, if your algorithm is allowing you to generate or create outcomes that are not prohibited, like if you had an algorithm for this situation that allowed you to pick 2 different sides or something, well, that wouldn't be allowed, would it? And also, it's really important that your algorithm only generate each outcome exactly once. Okay? If you write an algorithm that generates outcomes or the same outcome multiple times, then your algorithm is going to overcount the number of possibilities. So your algorithm needs to generate every possible outcome once and only once. Okay? The other property that a good algorithm must have is that the number of choices at a given step does not depend on the specific choice made at an earlier step. Okay? So, what I'm saying here is like, when you choose your side at step 2 in this algorithm, you have 3 choices. Okay? And you have 3 choices no matter which specific choice you made for your sandwich, right? Whether you went with the turkey sandwich or you went with the ham sandwich, you still have 3 choices for your side. In other words, the number of choices at step 2 does not depend upon the specific choice you made at step 1. And that is really important, okay? It's very easy to write down an algorithm where that's not true and not realize it. Okay, let's take a look at an example of basically a bad algorithm. Okay, I think this is it's a bad algorithm. Okay, so example, suppose we have 2 freshmen and 6 seniors. We wish to place 3 of them in 3 seats. Write a counting algorithm that generates all seating arrangements which alternate between freshmen and seniors. So freshman, senior, right, etc. So here's a bad algorithm that doesn't work. Step 1, choose who sits in the first seat. Step 2, choose who sits in the second seat. And step 3, choose who sits in the third seat. Okay, the problem is the number of choices in step 2 depends upon which specific choice you make at step 1. Okay, because remember that the freshmen and seniors are supposed to alternate, right? Freshman, senior, right? If you put a freshman in the first seat, then you must put a senior in the second seat, right? So here are the first 2 seats. If you put a freshman here, then you've got to put a senior in the next one, meaning that you have 6 choices at this step, right? You would have 6 choices for who goes in the second seat because there are 6 seniors, right? On the other hand, if you began with a senior, right? If you put a senior in the first seat, then you would have to put a freshman in the second seat, which means you would only have 2 choices for step 2 because there are only 2 freshmen. So the number of choices you have at this step, the number of choices you have at step 2 depends upon the specific choice you make in step 1. Namely, it depends upon whether you decide to put a freshman or a senior in the first seat. So this is a bad algorithm. Okay, this algorithm cannot help you. This problem is actually a bit tricky to solve. It requires that we break the outcomes into 2 separate cases. We'll talk about that later, or actually you'll see it in the worksheet. But for now, just understand that this is a bad algorithm because the number of possibilities or the number of choices at the second step depends upon the specific choice made at the first step. That's bad. Okay, so moving on, I want to talk briefly about why all this works. You know, why is it that, like, you know, counting the number of choices and then multiplying actually gives you the right answer? Well, let's suppose that you want to make a sandwich. Okay, you have 2 choices for bread, white and wheat. Let's suppose you have 2 choices for cheese, maybe Swiss and cheddar, and 3 choices for meat, turkey, ham, or tuna. Okay, an obvious algorithm for generating all possible sandwiches is given by step 1, choose the bread, step 2, choose the cheese, and step 3, choose the meat. That would certainly work. We can represent all possible sandwiches with a tree diagram, as shown below. So here's a tree diagram which shows you basically every possible sandwich that you can make, right? So step 1, you're choosing the bread, right? And you got 2 choices, white and wheat. So you've got like 2 branches of the tree diagram. And then once you do that, you've got to choose the cheese. Well, there are 2 choices for cheese, Swiss and cheddar. So these guys split again right into Swiss and cheddar. And then once you choose the cheese, you've got to choose the meat. And there are 3 choices for each of those. So each of these guys splits into 3 branches again. Now, how many total possible sandwiches, that is, how many total possible outcomes, are there? Well, you know, you can count them if you want, one by one, but it's pretty clear that there are 2 branches here, and then each of these branches has 2 branches, and then each of these branches has 3 branches, which means that the total number of branches is going to be 2 times 2 times 3, right? And that corresponds exactly to what I said about how to use a counting algorithm, right? You count the number of choices for each step, and then you multiply, right? So there are 2 choices for the first step, 2 choices for the second step, 3 choices for the third step, so 2 times 2 times 3. And this picture basically tells you why that works. Now, hopefully, with this in mind, you can kind of see why it is that your algorithm needs to be what I call the good algorithm. In other words, now you see why it is that your algorithm must have the property that, here's property 2, the number of choices at a given step does not depend upon the specific choice made at an earlier step, right? The reason why the number of branches here is just 2 times 2 times 3 is that no matter which bread you choose, right, white or wheat, you still have 2 branches here, right? 2 choices for cheese. And no matter which cheese you choose, you still have 3 choices for meat, okay? If you like, you could say that the tree diagram is uniform, right? 2 branches, 3 branches. No matter which path you go down, that's always true. That's why 2 times 2 times 3 gives you the right answer. On the other hand, imagine the following situation. Suppose you flip a coin twice. In how many ways can you obtain tails at least once? So, you know, you're flipping it twice. You want to get tails at least once, so that could be you get tails exactly once, or it could be you get tails exactly twice. Here's a bad algorithm. Okay. Step 1, choose the outcome of the first flip. Step 2, choose the outcome of the second flip. As we're going to see, the number of choices at the second step depends upon the choice, the specific choice for the first step. So here's a tree diagram for the situation. You have your first flip, and of course that could come up heads or tails, right? Now, here's the thing. If your first flip comes up heads, then with your second flip, you only have one choice. It actually must be tails, right? Because remember, you're trying to get at least one tails out of the two flips. So if your first flip is heads, then your second flip has to be tails. You only have one choice. On the other hand, if your first flip is tails, then on your second flip, you actually have two choices. You could do heads, right? You could choose heads for the second flip, or you could choose tails. And so what you're seeing here is the number of choices for the second flip depends upon the specific outcome of the first flip, okay? And that's a bad algorithm. And of course, you can see that the number of total outcomes is 1, 2, 3, but that's, 3 is not obtained in the fashion of multiplying the number of choices. You can see it doesn't make sense, right? 3 is not 2 times 2 or anything like that. So, basically this idea of just multiplying the number of choices all along the algorithm only makes sense if your tree diagram looks like this, if it's uniform, right? And it wouldn't work for something like that. So that is the idea. Okay. So I think that's all that I will say for now.